Hello and welcome to our presentation on cyberbullying detection. My name is Muhammad Anwer and my partner Ali Hasnat Khan is with me here as well. We approached this problem, this data set of cyberbullying, comments that were left online to bully people, and we we performed a classification task on it, and we used a variety of models to do that classification. The data set that we used had 20,000 plus entries, and they were fairly well labeled. Comment is the comment of the person who's bullying, and the label represents whether this comment is normal, offensive, or does it count as hate speech. And there's other features as well that are in the data set. We distilled it down to the comment, that being the feature, and the label being the label. That is what our classification would be. Any prediction that we're doing would predict if a particular comment would fall under one of these three labels: normal, offensive, or hate speech. What we did is that we cleaned and pre-processed the comments. We ensured the data quality was good, that there were no missing values. And in the case of the column that had missing values, we dropped it, and also particularly because it was not something that was a feature for our models. Here are some word clouds, and be warned, there are some offensive words here. Unclean data looks like this: of all comments, offensive comments, normal comments, and hate speech comments. And the clean data, very similar, but more emphasized, more amplified on certain words and whatnot. Going forward, every of the offensive words that are found are going to be redacted. Here are the pre-processing steps that we performed on our data. We cleaned the comments by removing the stop words and punctuation. We limitized the text, removed non-alphabetical characters like numbers and emojis, and removed the phrase age ago. Age ago was hours ago. That's something, whichever the data set was collected from had a lot of those phrases. So removing that helped in the quality of the data. We handled the columns that had missing values like miscellaneous, and we removed that column. Also, again, we're not featuring that column in our model. We used feature engineering as part of the pre-processing. We vectorized the comments, the clean comments section, the clean comments. We vectorized them using TF-IDF, and that gave us a numerical representation of those words. And then we encoded the labels: offensive, normal, hate speech, with label encoder. And then we divided the data into training and testing sets. As you can see, the encoding resulted in the labels that were in the data set as normal, offensive, hate speech were then encoded as 0, 1, and 2. And that is something that is necessary to prepare the data to be provided to the model. And here is the data before it was clean. As you can see, there's emojis, there's random, random characters there. After cleaning, a lot of that text was removed. I'll turn it over to my partner Ali to talk about Model 1 XGBoost with default training set.
The first model that we use for classifying whether the comments are normal, offensive, or hate speech, we use XGBoost. XGBoost stands for Extreme Gradient Boosting. It is a scalable and distributed gradient boosting decision tree library. So firstly, we use default hyperparameters, and we got a training accuracy of 76% and testing accuracy of 65%. You can see the confusion matrix. We are getting some good predictions, but there are very wrong ones. Let's test them on some unseen data. Out of 4 examples that we provided to our model, we got 3 correct ones and 1 was wrong. After the default hyperparameters, we tried grid search to hypertune tune the hyperparameters. Firstly, use um, we use the n estimators, max step, learning rate, and some other hyperparameters. The objective was to maximize model's accuracy. Next one. So we saw a slight increase in training accuracy, but the testing accuracy was almost the same, and confusion metrics also remained the same. Then, in the first model, the training set that we used had some imbalanced classes, like shown in the previous slide. Like in this slide, we can see that the first class has uh, the highest number of rows, while the value 2 has the lowest number of rows. So this can cause some biasness in our model. To avoid that, we use SMOTE algorithm to upsample the minority classes. On the right, we can see that all of the rows are equal. So we trained the XGBoost on this data again, and we got a higher training accuracy and a higher testing accuracy. Next slide. But the results on the unseen data were the same. We got 3 correct out of 4. Next one. We trained tuned the hyperparameters using grid search. Next slide. So we got a training accuracy of 80% and the testing accuracy of 67%, which is a 1% increase than the previous model. So we can see that tuning improved our result. Now Mohammed will continue.
Thank you, Ali. Model number 3 is the good old logistic regression. And this model is the one that gave us the best results. We started off with a basic logistic regression from sklearn without any tuning, just the default version of it. It had a decent training accuracy of 76% almost, and a very good testing accuracy of 62.9%. The confusion matrix tells you that the results are largely good and trending towards normal, classifying things more as normal, and the hate speech, showing that there is a tendency of the model to classify those in a manner that's maybe overly representative. The results on unseen data, the same phrases that we've been using, was very good. It got all of them right, particularly this comment, which is an offensive comment. It correctly detected it to be offensive. So this is the basic logistic regression, after which we performed the hyperparameter tuning of this model with grid search CV. And grid search CV is a technique that allows to tune the hyperparameters of a logistic regression model in a variety of parameters. You provided a parameter grid, and it affects the regularization. It affects the strength of the regularization, and also it affects the optimizer that is being used as part of the model. All of these things were used to tune the model. The results were quite similar, a small uptick in the testing accuracy, but largely the same. And that was model 3. Model 4 was a more advanced and more involved model, an MLP implemented using PyTorch, a fully connected neural network. It had the following architecture. The in features were 5073. That's the number of features that were being used as an input in the input layer, and the output at the very end was 3, because we are classifying our output as either offensive, normal, or hate speech. And in between between the layers, the hidden layers, we're using the ReLU activation function, and we also added a dropout with a 50% probability to add a little bit of regularization to the mix. The training accuracy was fantastic, almost 100%, 99.42. However, the testing accuracy was lower than the logistic regression. It came out at 57.53, indicating that there is a overfitting of the data that was taking place. And as we ran it on unseen data, it got 3 out of 4 right. It even classified this normal comment as offensive. Perhaps the model is a little bit woke or something. The following hyperparameter tuning was done. We added a dropout after the first 2 ReLU functions and also added another hidden layer. And then for the other hyperparameter tuning, we changed out the Atom optimizer and swapped in its place the SGD optimizer with a lower learning rate and weight decay and higher epochs to see if that would make a difference. And it did not make much of a difference. The first tuning did not make much of a difference. The accuracy was still very high. The testing accuracy, unfortunately, did not go up much more. And in this particular situation, what we had done is that we had added multiple layers, an additional hidden layer to the model itself. The final model we used was Spacey. Spacey is used earlier on in the pre-processing step, the lemmatization, the removing of stop words, etc. But also Spacey is used to run a classifier. The training accuracy of that classifier was very high, a good 74%, and the testing accuracy was among the highest at 63%. When you ran it on unseen data, it again came out very similar to the first 2 models and the MLP, the 4th model, in which it got 3 out of 4 right. And this particular one, the comment that was offensive, it did not get it correct. What we did to tune this model, the hyperparameters, is we increased the batch size and epochs to allow the training of this model to be longer. Also, the model was trained on the entirety of the data set here in the hyperparameter. In the original training, the model was trained on a subset because the time it was taking was quite significant. But despite that, it didn't make much of a difference in the testing accuracy. Also, we lowered the dropout rate to 0.1% because the loss was quite significant. This is perhaps something that could minimize the loss and improve performance. However, what it resulted in is that the training accuracy went up quite significantly. However, the testing accuracy, in fact, did not progress forward, and that resulted in a worse result at the end. Similarly, for the dropout rate here, we had actually, excuse me, in that particular one, this particular slide that we had previously was highlighting the parameter tuning of increasing the batch size and epochs. And while that resulted, while that resulted in a, let's try that again. The increasing of the batch size and epochs, while that resulted in a higher training accuracy, it resulted in a lower testing accuracy, alluding to the fact that perhaps there is some overfitting taking place. Reducing the dropout rate did minimize the loss. As you notice, it went from the 30s here to the 11s and the teens, and that was good, and the training accuracy remained high. However, the testing accuracy did not budge and remained at 60%. And you can see from the confusion matrix that the results are trending more here towards hate speech, that this model is perhaps keying in on hate speech as one of the, maybe there's some overfitting here on that particular label. And again, when we ran the model, we saw similarly over here, it got 3 out of 4. That is our presentation. Those are the 5 models that we used on this data set of cyberbullying. This was an excellent project. We had a lot of fun with it. Thank you for listening to our presentation.